In this video you will learn about Ohm's law, the famous law which you surely have heard about in school, which connects current and voltage via something called the electrical resistance. And using an example we will find out how an unknown current in a circuit can be computed from a measured voltage and also a known resistor value. And you will also learn here what ohmic materials are and why Ohm's law does not always apply. My name is Andreas from The Fearless Engineer, and here we go. Now, before we look very closely at the famous Ohm's law, let's look at a very broad definition taken from a German dictionary. There it says that Ohm's law is a physical law established by Georg Simon Ohm, which describes the relationship between voltage and current in a circuit. If you have watched any of the previous videos, which we have used to build up to this point where we can derive the relationship between current and voltage based on a number of simple parameters that describe certain aspects of a conductor, then you will clearly have the formula already in your mind. If not, let's quickly recap the main concepts which we need in order to understand what's actually behind Ohm's law. We have seen already that current and voltage are connected by the material properties and geometric properties of a conductor. For example, a copper wire. Now both parameters, second point here, both parameter groups are combined to form the conductance value, which expresses how well a body conducts the electric current. And this has already been elaborated on in one of the previous videos where we looked at the concept of conductance and also conductivity. And conductivity is only about material properties, and conductance incorporates the geometric properties as well. And it's represented by the letter G, if you probably recall this video. The third point, this is the reciprocal value of the conductance, and which we look at, and this is called resistance. The resistance, expressed by the letter R, expresses how poorly a body conducts the current. Basically, it's as simple as the opposite of the conductance. By using the resistance, we express how poorly a body conducts the current. And obviously it's driven by the same parameters which make up the conductance, but only in an inverse relationship. And now with all these items in place, with all these knowledge nuggets, so to speak, we can now express Ohm's law in a very simple fashion, which you can see here. Ohm's law basically establishes a relationship, but you have to be careful in terms of what this relationship looks like. It's a linear relationship. We will get more deeply into this in a few minutes. A linear relationship between current and voltage, and it helps you to calculate an unknown quantity using two known quantities. So for example, this is Ohm's law, and in this law you can see the current on the left side and the voltage on the right side, and the inverse of the resistance here in between the two. You can also use conductance in this context here, but this is not the form which you find in the literature. We want to express how poorly something conducts electricity, and this is why we are using the letter R here. And if we, for example, know the resistance of a material, and if we also know the voltage drop across this material, then we can compute the amount of current flowing through this conductor very simply by applying this formula here. And this is Georg Simon Ohm. He lived in the 18th, 19th century, and he was a very famous contemporary of physicists such as Kirchhoff and many others, which laid the foundations of electricity in this very interesting time in terms of the engineering sciences. And the unit for resistance which we use is the ohm, which we have used before in one of the previous videos where we introduced the concept of resistance. And now you understand why it's named after Georg Simon Ohm, because he was the one to define this relationship and to devise a certain number of experiments to really verify the validity of this simple relationship between current and voltage by connecting resistance in between. And with the help of Ohm's law, we can calculate all three parts of the equation, given that we have the other two, which you can see by this very helpful triangle here. So the major aim of this triangle here is to help you recall the correct shape of Ohm's law. Let's start with the simplest relationship, which is found in most school books, which says that the voltage drop across a resistor is given by the product of the resistance of this resistor multiplied with the current through this resistor. So voltage drop is resistance times current. You can remodel this relationship to compute the current through a resistor, which is the voltage drop across the resistor divided by its resistance value. And if you look at I, you can clearly see that U is in the numerator, the voltage is in the numerator, and the resistance is in the denominator. You can do the same for the resistance value. If you want to compute the resistance from voltage drop and current, you can clearly see here that U needs to be in the numerator and I needs to be in the denominator because of its position here in this triangle. So this is a very helpful way of helping you recall the three forms of Ohm's law. Now let's look at an example circuit here. In this circuit we have two resistors which are connected to a battery. This is a typical 9-volt battery. We have two resistors here which have an identical color code, and if we know the first one, which is 4.7 kilo ohms, so 4,700 ohms, we also know the value of the second one. It's supplied with electricity through the electron flow emanating from the negative terminal of the battery, which then flows back to the positive terminal. So we have an unbranched circuit here. In this unbranched circuit, we can use Ohm's law in this form here. We want to learn the amount of current flowing through the two resistors, and in order to do so, what we need to do is we need to make a voltage drop measurement, which we can do by using a multimeter such as this one here, and by connecting its probes to the input and the output connector of this resistor here. And if we measure a voltage drop of 4.5 volts and we know the resistance value, we can compute the amount of current running through the resistor. The resistance value is not going to be 100% precise because there's always a tolerance associated with the resistor, but assuming this was a perfect resistor and a perfect voltage drop measurement, we can use Ohm's law to compute this value here, which tells us that the battery right now is piping 0.96 milliamps through this little circuit here. Another angle on Ohm's law would tell us that 1 ohm is the resistance through which a current of 1 amp flows if we apply a voltage of 1 volt to a certain component. This is the form of Ohm's law. Resistance equals voltage divided by current. And if we simply insert these values here, 1 ohm, 1 volt, 1 amp, we get this relationship here, which gives you a better impression of the meaning behind Ohm's law. Now secondly, if we divide the voltage by the current I, we assume that this is a constant relationship which is independent of the current, and if this is the case, we say that the material under investigation has an ohmic behavior. You can see this indicated by the green straight line here, which increases the current flow when we increase the voltage. So let's say we have a voltage of, let's say, 5 volts, which might be this value here. Then we just move upwards until we intersect the green line. We move left until we intersect the y-axis, and then we get the current. And if the material is ohmic, we can say that once we increase the current, the relationship between these two is going to be the same. We can basically say that R1 represents the slope of this straight line here. There are some materials which are non-ohmic, and with the red curve here you can see that the relationship seems linear at first, but then the slope decreases further and further. And for large voltages, this means that even if we increase the voltage to a large extent, we wouldn't get a very strong increase in current flow. This is indicated by this material here. And for such a relationship, we cannot simply apply Ohm's law under all circumstances. So the main idea of this video here was to give you an overview of this very simple relationship between current and voltage given by material properties, which are represented by the concept of resistance. Also, you have learned that there's a difference between materials for which these material properties do not change with increasing current flow or increasing voltage. These are the ohmic materials, and the other ones which change their behavior depending on the amount of current flowing through them, these are the non-ohmic materials. This is a severe limit of Ohm's law, and in one of the upcoming videos we will look more deeply into this limit and see if we can find ways of circumventing this limit in order to find a way to use Ohm's law even in a context where we have a non-ohmic material. That's all for now. If you have any questions related to this video, don't hesitate to drop me a comment down below in the comment section. Also, if you have any suggestions for future videos which you want me to make, please also leave a comment here. I wish you a nice day now, all the best, and see you next time here on The Fearless Engineer.